of the algorithm. So let me select the so obviously there are 3 clusters, so we can use the DB scan. The EPS is the 10, the size of 10. Number of points is the 5. Okay. And start. It's too fast. Once again. So it starts, it moves to find the reachable. Okay, next. So this will be considered the outlier. Then it moves to this one, then it finds the reachable. And this one and this one will be considered and directly connected because you can find reachable. The point. Okay. Then once this one is done, you will then the test the other. Definitely this one and this one will not be shared the cluster. And move to here. Okay, then we will add the clustering. What about k-means? So without pause. And clear the data. How many clusters? We found 1, 2, 3 clusters. Okay? So even though we have the 3 clusters, one is here, another one is here. Why? K-means find one of the centroid here. Because it focuses on outlier because of the shape of the cluster. So from here, the closer one is this one and this one. This one does not include this point as the same cluster. And this one will be far away. Doesn't consider the relationship of this. But DB scan, density based, consider the relative relationship. Because it's based on the density, then it can clearly find that this one as the one cluster bar here. Find this group as the one cluster, this group as another, this group is another one. I think here is looks like the 5. anyway. We can apply K method. So 3. It takes a long time, so we can select other data set. I think there's something wrong. So forever. Okay, so anyway, so that demonstration shows the difference between the DB scan and the partition-based approach. Why don't you test with this applet to understand the algorithm? Okay. I'm going to skip the optics, so but idea is we can visualize the cluster as into the two-dimensional cases using the distance, like this way. Also, you can test the algorithm of the optics. It's also density-based using this link. Why don't you test it later? Okay. I'm going to skip the grid part. Then evaluation. Then after, no matter what types of the clustering algorithm you have, anyway, we need to evaluate the clustering algorithm. The main problem is, one of the main problems of the clustering is how many clusters we have. The empirical result shows is the square root of the half of the data, but it's just the empirical result, not in general. So that is one things that you need to evaluate. Okay, there are different ways of the method. So you can use this one, or you can use the how many curve of the sum within the cluster variance, and also when you evaluate the quality of the cluster, so if you had the ground truth, as I mentioned for the final project, we can use such a ground truth, okay, labeled data. So for example, if you can do the training and the testing, so we will learn the training and testing details in the classification. We can use the labeled data, the ground truth for the training, then test it. However, sometimes we cannot have such a ground truth. Okay, if the ground truth is not available, how can we address such a problem? At that time, we can have the goodness measure. Goodness measure means, like for example, if we are using the model base, the model itself is our goal. How much closer to the ideal case? Okay. Or sometimes, what is the variance? How much more compact for the cluster? So because we do not have the ground truth of the data, sometimes it's very subjective. Even though we can ask, for example, medical doctor. So ask the medical doctor whether this is the cancer disease, cancer positive or negative positive. Do you believe the medical doctor is always 100% correct? No, definitely not. So when we cluster such a thing, we are judging the quality of your clustering algorithm by using the shape of the cluster, which is called the goodness measure. So our goodness measure is for example, the ideally circle. How much close to each other? So ideally circle. So that's the just example. Depending on the goodness measure, so we define such a goodness measure to judge, to evaluate our clustering algorithm. Okay? Even though for each point, even though we do not know whether this one belongs to the positive or negative, by considering how the shape of the cluster, we judge how much this is close. Anyway, our algorithm, no matter what type of the clustering algorithm, our idea is if they are similar, belongs to the same cluster. Distance is far away, right? If they are dissimilar, they belong to different. So based on that idea, we can define the goodness measure. Then based on that goodness measure, we judge, evaluate our cluster. Okay? In case we have the ground truth, so if that is well, based on that ground truth, we can judge for that cluster. Okay, then why don't you continue? We have just 20 more minutes. If we want to go to the restaurant, we can go to. Okay, so so this is a summary of the chapter 10. Why don't you test the optics algorithm also using the given URL, so then you can easily understand the optics algorithm. You don't have to worry about too much the grid-based algorithm, which is not frequently used. Okay, so for the evaluation, so we did. So in this, the advanced method of the clustering algorithm, we will take a look at mostly the model-based clustering. Okay, and the other, the clustering, the graph and network. So we will see the two of them, and the other, so you can understand by yourself. So actually, there are. What is a fuzzy, by the way? Before we start the model-based approach. Fuzzy means not clear.
Confusing.
So when we apply the k-means algorithm, so when we have so we can ideally, our expectation is two cluster. So if we select the initial point like this one, so we decide whether this point belongs to this centroid or this one. So this is close. So we can say this is the part of this one, and this one, this one, this one, this, and this one, this one, this one, this one. Then using that membership, we will decide the new centroid and new centroid, right? This is called hard membership, which means this point should belong to either of them, only one cluster. However, why don't we consider this one? So it's a little bit close. Let's say this is the 1 inch, and this is 0.9 inches. Just 1.1 inch difference. But because of that difference, we need to say this one belongs to here. Then this point, centroid, move to a lot to this point, because it's the average of this one. At that time, what if this one is half of that? Half of the membership is this, half of the membership of this. Then ideal centroid may not change a lot, because we consider soft membership. That soft membership is called fuzzy set. Fuzzy algorithm. Fuzzy algorithm means, so when we decide something, the problem, when we decide any decision, when we decide something, it's not hard decision always. Sometimes 90% he purchase the camera and 10% for the cell phone, right? So we can the predict for future purchase by him. So 90% camera and 10% for something. So always it's a positive problem. It's a static probability. That is called the fuzzy set and fuzzy cluster. So if we consider such a soft membership, fuzzy membership is a fuzzy cluster. In your second project to implement the k-means algorithm, you will implement the fuzzy cluster. The only different thing is the membership, whether you are going to use the soft membership. So then we can generalize such a soft membership to the probabilistic model-based clustering. Idea of the model-based. Whenever you see the model-based approach means it's a statistical model. Okay? Model means it's ideal case. It's not true, but it's ideal. Like the fashion model. Fashion model is it's not realistic sometimes, but ideally. So we try to fit the new clothes to the ideal body. Okay? We don't need a beautiful woman or beautiful handsome man for the model. We need ideal body to show up our new clothes. So similarly, when we are using the model-based clustering, so sometimes it's not realistic, but it's the ideal model of the data. Idea is when we have the more and more data, it will form something statistical model. That is one of the example that we can find such a statistical model is the presidential campaign, for example. So by selecting the 1,000 people, we can predict for the result of the presidential campaign. Because using that, the 10,000, the example, we can imagine, we can draw the statistical model. So idea is the same thing. When we cluster, why don't we model such a cluster for statistical distribution? At that time, we can use Gaussian distribution for the probabilistic density function. Okay. The main reason is the central limit theorem. Any types of the statistical model, statistical distribution will form the Gaussian distribution if we order random variable by the frequency. Okay. Simply, why don't you imagine if any distribution, any types of event, there might be most frequently happen. Okay, that form the mean value and rarely happen. There might be the data rarely happen. That is the sign mean. Okay, rarely happen. So that from the normal the Gaussian distribution. Normal distribution, if you adjust the mean value to the 0, that is the normal distribution. Okay, then usually that we have the 2 or more cluster. So which means we have the 2 or more Gaussian distribution. So our goal, our problem is change it to find the such a parameter value of each distribution. In this case, we have 2 model. Okay, 2 statistical model. So we try to find such a 2 statistical model. Sometimes we have the local minima, like this one. So sometimes we can consider this one as another. Sometimes not. It's the same problem. We should know number of the distribution cluster. Okay. Then any types of model-based approach is the same thing. Our goal is to find such a parameter value. So that parameter value can represent the cluster. So each cluster means the Gaussian distribution. So each Gaussian distribution can be described by the mean and variance, which means each cluster can be represented by the mean and the variance. So how can we find the parameter value? Using the likelihood function. Likelihood function is the product of all the value that apply to the probability function, which is the Gaussian distribution. Like where is that? In the Gaussian, that is this one. It's a probability density function. This is a Gaussian distribution. If you want to use the different model, then you can replace this one by the new model. But because of the central limit theorem, so mostly we use the Gaussian distribution. Then there is a product of the probability density function with the weight. Okay, so weight of each point. Okay, so it's a weight of each point that is considered as the membership. Okay, for each cluster, what is the membership? It's kind of weight. So for example, this one is not hard membership, so 30% and 70% to this one. When you have the three model, 10%, 20%, or 70%, something like that. That is the weight function of the here. And the F is the probability density function. In case of the Gaussian, so we can use this one as it is. Okay, then we can find the argument, that is a parameter value that maximize this product. Okay, that is our goal. So if we have several 2 or more Gaussian models in our data set, that is called the Gaussian mixture model. So when you see the Gaussian mixture model, or if you want to use the many Gaussian model, you can say this is the Gaussian mixture model. So Gaussian mixture model means we have many clusters. Okay. The problem is, how can we find? So in this case, this is a product. From n is the number of items, and k means number of Gaussian model. In other words, number of cluster, and this is the probability density function. So sum of this one, then the product. Pi means times the next first. So this one means it's a membership to from 1 to k for the first data item. Then times the product of the next item up to the n. Then we try to find the parameter value that maximizes this value. This is the expectation value. So we try to maximize. Maximize means fit to our model. Okay. So we can use the 2 steps. One is the expectation, which is called the E step, and next one is the maximization. The E step, for the cluster, each object assigned is a kind of assignment to the cluster. So it's the same as the K-means algorithm. First, we should have the initial, the centroid, initial point. So let's say this is initial. So we assume there are 3 Gaussian models. There are 3 clusters for each point. Decide what is the membership. Okay? That is the E step, expectation step. So it can be 10, 20, 70%. Because it's based on the fuzzy, okay, soft to membership. Because it's a probability. Then maximization means the product of using such a membership. Then we can product. Then that determine using the E step and M step, we can find the parameter value until not change it. So it's an iterative. So iteration, E step and M step. So that is the reason it's called the EM clustering algorithm. EM clustering algorithm is the same as the model-based approach. So it consists of the E step and N step. Okay. So fuzzy clustering is special case of the EM clustering algorithm also. Okay. Our goal is to find the number of the mean, number of the variance. That number determine the k number of the cluster. So during the E step, for each object we can determine the membership. It's kind of the membership, that is the probability that each object belongs to each cluster distribution. It's kind of a way. How can we compute that distribution, the membership, using this one? And during the M step, we can apply the likelihood function. It's a product. Okay, so we can find the parameter value of the U and the mu, the mean value and the variance, using this function. So I'm not going to explain details how to prove this one. So if you want to know how we can get this, you can check look up the statistic, any statistic textbook. You can find the EM cluster. The EM, it's not clustering in terms of the statistics. It's the expectation and maximization. It's usually part of the likelihood function. You can find that the proof of how we can get the mu and the variance. Benefit. One, it's not mentioned here, but one of the strengths of the EM clustering algorithm is it's invariant. In other words, very strong for missing data. The k-means, ideally like this. But if we have some missing data, like this one, sometimes it doesn't work very well. As you have seen, it always try to find the closest one. Okay. However, using the EM clustering, even though we miss some data, because we model the cluster like the Gaussian distribution. So even though we have the missing data, it's not very sensitive for the missing data. So that is one of the benefit of using the EM clustering algorithm, because our algorithm is based on the model, statistical model. So even though we have some missing data, as long as it forms the cluster, the distribution is okay. One of the main problem of the EM clustering is not the problem of only the EM clustering, but k-means or any iterative based iteration. Any algorithm that requires iteration. Iteration means keep doing the same thing until the not changing converge. Okay? So such an algorithm is sometimes converted to the local minimum. Local minimum means, for example, how many clusters? Actually, 2 peak. This is kind of outlier, but sometimes if you select the centroid over here, it tries to find this as the cluster peak. This is called the local minimum, local optimum. So it tries to, depending on what? Initial point. Depending on the initial point, it tries to converge to the local, the optimal, local maxima. So you should we are aware of such a problem. So how can we overcome that? Run many times, then average, or the initial, selecting the initial point. Sometimes randomly select. So it's if you select many times random, so it can be overcome that one. Okay. So same problem as the partition based. We don't know what is the optimal value of the k. That's always the same problem. Most of all of the clustering algorithm has the same problem. How many? The cluster. Okay. So that is the reason I like the binary problem, positive and negative. and 0 or 1. So bisect. Okay, so you can consider such a thing. And also it's computationally very expensive. It's for each iteration. Okay, conversely, you need to check for each point and the membership. So it's a big notation n k n square k n square k. Okay. But another benefit of the EM clustering is we can simplify the problem of the clustering as a parameter value. Gaussian need only 2 parameters. So as long as you find the 2 parameter value, it's a cluster is done. Okay. Reasonably, in practical point of view, EM clustering is working very well. K means it works, but not always. But EM is better than this one. So when I was a PhD student, it's kind of a trend. EM clustering was very, very popular. Few years later, support vector machine. So we will see later support vector machine, SVM, is currently the most popular clustering algorithm. Support vector machine can be used for the classification also. It can be used for the clustering also. So we will see the support vector machine later. Okay? But still, the EM clustering is used. One of during my dissertation defense, the PhD defense, one of the committee member asked about why you select the EM clustering for my dissertation. I used the EM clustering. So at that time, what she wants from me was it's good for it's not the variant for the missing data. Okay. Next class we will continue. I'm going to skip the high dimension. Then we will continue from the clustering graph and network data. Okay. Unfortunately, I cannot cover each and every algorithm.